Good morning from here, from Rochester, New York, and good afternoon to all of you attending the meeting in Łódź. It's a great pleasure for me to be a part of this meeting, and I would like to thank Krzysztof Pomorski for inviting me and encouraging me to present our work on superconducting single-photon detectors. This will be a somewhat historical view. I would like to show how these detectors over 20 years revolutionized quantum measurements, all measurements related to single photon detection. As I was introduced, I was the University of Rochester, New York, and with the departments of electrical computer engineering, physics, and the material science program. Before I move on, I would like to give you a brief overview of my ultrafast quantum phenomena laboratory. The lab is experimental, and talk will be strictly experimental, and is dedicated to basic and applied research on ultrafast phenomena. This is an interdisciplinary effort, and we try to combine condensed matter, quantum electronics, quantum electrodynamics, and optics, and nanoelectronics. Here at the bottom is the motto of our group, and I really like it. So I quoted this from Paul Davies from '96, that the 19th century was known as the machine age. The 20th century actually, went down as information age, and he believes that 21st century will be the quantum age. And I certainly agree with that point of view, and I even hope that when I joined University of Rochester, I joined the electrical engineering department. And over the years, we switched to electrical and computer engineering department. And I hope that before my retirement, we'll be actually changing name again and moving into electrical, computer, and quantum engineering department. Actually, we have a quantum engineering concentration as part of our MS program. Here's the group of characters from the University of Rochester over the years, graduate students who graduated and postdocs working in my research group. Our main collaboration was the Delft University in the Netherlands with the Institute of Physics Institute of Electron Technology in Warsaw. Now this is part of the Łukasiewicz network. And all the initial collaboration and start of the program actually was in direct work with a Moscow State Pedagogical University. Of course, unfortunately, that collaboration is no more active. So here's the brief outline. So I'll give an outline of photon detectors, starting with very fundamental question: what is a photon? And what we would like to get from ideal photon detectors, single photon detectors. Then I will move into superconducting single photon detectors, starting with the intro to superconductivity and non-occurring response. And finally, I'll give you a number of applications, starting with the very first one, which was debugging of silicon VLSI chip, and moving to most recent in terms of quantum cryptography and quantum communication. Okay, so there are two basic classes of single photon detectors, single optical photon detectors. There are semiconducting devices and silicon SPADs, so single photon avalanche diodes are the most prevailing ones. And as you can see, they work well, and they're well positioned in visible range because, of the energy gap of silicon. And if we move to communication wavelengths like 1.55 micron, then you need to move to a different material, which is InGaAs. And the InGaAs compared to silicon is much less developed, and there are a number of issues plaguing those detectors. But in general, all those avalanche photodiodes have large number of false or unwanted counts after pulsing a relatively low kilohertz speed because of after pulsing and unwanted counts. They also require gating in order to eliminate the excessive noise. Their obvious advantage over, let's say, superconducting detectors is that they work at room or near room temperature. On the other hand, okay, so things changed, and I call this slide a prologue, change when my research group and group from Moscow State Pedagogical University, when we published the first paper on picosecond superconducting single photon detector, you have a page from Applied Physics Letters and an abstract. And what I would like to stress that at that time, there was a very productive collaboration between the United States and Russia. You can even look at this special grant which we obtained, and it was the U.S. Civilian Research and Development Foundation for independent states of the former Soviet Union. So times were different, but of course, you know that year is 2001. And this is how that detector looked like. It was just a single stripe, about 1 micron, slightly over 1 micron long, about 3-4 nanometer thick, and about 200 nanometer wide. So we could observe the fact when photon managed to hit that stripe, and I will explain this in detail later. So going back to the main flow of my talk, the question is, what is a photon? And of course, the early concepts that those are like small bullets or darts of energy is gross simplification. Photon concept relies on 4 basic elements. So you have transport of energy and momentum through the space. Well, that's a famous particle wave duality. On the other hand, photons have 0 size. So they are point-like localization of energy. Photon can interfere with itself. And another very spectacular feature is that electron-photon interactions are 0-time interaction. There is no any kind of interaction time in electron-photon interaction. That comes with the simple fact that photon does not carry stationary mass. Okay, so those are and now in quantum information, people talk about optical quantum computing, and one reason is that the photons can be very easily regarded as a quantum state, and they can easily be generated, or quantum states can be generated with single photon sources in detectors. So quite often in quantum information jargon, photons are called flying qubits. And so here's the recipe, or here's the wish list, rather, of the best possible single photon detectors. So we would like to have, of course, quantum efficiency reaching 100% or being 100%. In general, very broadband operation from UV to mid-infrared, low or dark counts, or as low as possible, with no false unwanted counts, and no after pulsing, and a very high fast picosecond response time, signal rise and recovery, with no dead time between the counts. And that's extremely important in any kind of quantum communication based on transmission of single photons. You would like to have as high rate of transmission as possible. So you need to have a detector. You can have emitters which emit high rate single photons, but you need to have detectors being able to catch one by one of those photons. Finally, some additional features which are not directly related to communication, but useful from the physics and metrology point of view, is the energy resolving capability, photon number resolving, and if possible, also photon polarization resolving capabilities. So example where single photons are useful and needed, well, all the quantum optics and then quantum physics, that's the main topic of this conference. So this is kind of obvious, dealing and understanding entanglement, linear quantum computing. Extremely important aspect is metrology, where we would like to have way to define, let's say, single and qualify true single photon sources. So you need to have a true single photon detector in order to be able to qualify true single photon sources. And in the engineering and information technology, quantum cryptography based on transmission of single photon is the best known option. Other is quantum communications, again, using flying qubits as means of communication. Finally, it's not strictly single photon, but far infrared astronomy, moving from mixers into fast single photon detectors is expected to improve our observation of a universe in far infrared range. And the new element is medicine and optical tomography, and then all aspects of optical imaging and optical tomography is based on the fact that, visible light our body is not really transparent to visible light, but in some elements, you can still get some transmission of photons, but then transmitted flux, it will be on the range of few photons or even single photons. So you need to have single photon detectors. This is a general feature of single photon detectors where people talk about photon starving objects, or in other words, all very faint light because single photon detector obviously is the ultimate sensitivity. Okay, quick comparison. I focus on semiconducting detectors now. In superconducting detectors, as I will show, a single photon creates a very large gain, and typically on the order up to like 2,000 gain in terms of one photon creates up to 2,000 excited electrons. Response times are in picosecond. Dark counts are essentially negligible or almost negligible. And that comes from the fact that, of course, superconductors operate at low temperature. Our workhorse is niobium nitride, so we operate detectors at 4.2 Kelvin and even lower. But having said that, and making virtue out of necessity, that makes all measurements in a very quiet, low dark count environment. Finally, since the background is so low, no gating is required, and you have simple biasing source. Okay, so let's move to superconducting single photon detectors. A brief introduction, and I put a superconducting transition of yttrium barium copper oxide. The first superconductivity was discovered by Karmelik Hans in 1911. He developed method of liquefaction of helium. So having liquid helium available, he measured electrical properties of mercury. And he picked mercury because mercury is a liquid at room temperature, so it was easy to distillate mercury, make it extremely pure. So that's why he picked mercury. And well, the curve looked similar, but that was at 4.2 Kelvin. He observed a dramatic drop of resistance to the value, which was essentially zero. So that's how it was discovered. why BCR is interesting, not necessarily for our detectors, but as a big jump in terms of critical temperature, because you see we are well above the liquid nitrogen temperature. Basically, I list here, and the main property of superconductors is sort of in semiconductor analogy. We can talk about the band gap between the Cooper pair state, and this Cooper pairs are pairs of two electrons, and they're physically spaced some distance, but they are kept together, and there are two electrons of opposite spin and momentum. So Cooper pairs as a particle are bosons. So they can occupy a single electronic state. And so that's why we have no scattering, and we have superconductivity, zero resistance. And they are separated. So their coupling energy can be regarded as a gap separation from normal electrons. So if I deliver energy enough to energy gap, which is called 2 delta because it's counted per electron, then a pair is broken and two electrons are created in the conduction band. So that's the, in simplest term, how you can excite superconductors, and you can switch them from superconducting state into resistive state. For those of you, and I don't think there are too many of you electrical engineers, you can look at superconductors as a parallel connection of perfect inductance, and that's where the Cooper pairs will flow, and at final temperature, normal resistance, that where unpaired electrons are going to flow. Of course, at 0 Kelvin, we have only the supercurrent flow, and at critical temperature, if we cross critical temperature, that branch is is open, and we have only simple resistive flow. Okay, so here's a schematic of how electrons, how photons can create perturbation, create excitation in superconductors. So once again, we have a Cooper pair, and if I apply optical photon with the energy much greater than energy gap, I can break that pair and create two excited electrons. Because of conservation, then one electron will be relatively low energy, and the other will go way up into conduction band, and will relax very quickly through electron-electron interaction, electron-optical phonon interaction. Finally, it will kind of thermalize. Those electrons will thermalize near the bottom of the gap, and they will start to drop with emission of a phonon, reforming Cooper pairs. But you can see that phonon energy is large enough to break, once again, a Cooper pair. Well, because energy of that drop is exactly a little over of the energy to break the pair. So basic photoresponse of superconductors is a picosecond extremely fast relaxation, followed by very slow, so-called the phonon bottleneck, which will be, well, nanosecond, even to, well, roughly in the order of nanoseconds relaxation. So please keep that in mind, that if I excite my superconductor with optical photons, I break superconductivity, I create unpaired electrons, and that would create voltage. That would be just like jump from this arm will be broken, and then you have resistance and you have voltage. So we'll be looking at the switching between zero resistive state, and because if this arm exists, it shunts that resistance between zero resistive state and the normal resistive state. And obviously, if I have a bulk piece of a superconductor, the local photon perturbation will be small unless the number of photons is very large. But if I have an extremely narrow, thin stripe, and my stripe will be on the order of few nanometers, and extremely narrow stripe, then if I bias this stripe with current, even a single photon may create large perturbation enough to push the current outside, and this way reach the critical current and turn essentially, so there will be like a resistive barrier. So again, we switch from 0 voltage state into resistive state. But since the perturbation is very, very small, that hotspot will relax on the order of 100 to 300 picoseconds. So once again, I have a switch which is shorted, and then upon photon absorption will open up, and it's a essentially geometrical effect. So my stripe, my constriction is so thin and narrow that even as perturbation delivery of an energy of 2 electron volts will create all those secondary electrons in large number enough to create a resistive, local resistive state. So you can see that superconducting order parameter will be suppressed and in the resistive state form. I hope it's clear, but I'd be happy to spend more time on that. So I'm back to my first device. There was a single stripe, and once again, this worked exactly according to this schematics. We would have superconducting state, 0 voltage state, and I'm sorry. And when the photon stripe absorbed a photon, it would switch to resistive state, which corresponding to like 2.5 millivolt. This is large enough to amplify using cryogenic amplifier, or even room temperature amplifier would amplify the signal, and that can be detected and collected and do everything. Okay, so obviously this kind of a single wire, a single stripe, practical exhibited very low efficiency. I mean, stripe was efficient, but not all photons wanted to hit my stripe. So number of photons hitting stripe and producing a response was relatively small. So the first step was to make an extensive meander. So you can see the black is the niobium nitride, and you can see it's 10 by 10 microns, and you can see here this is in a very extended. So that meander is on the order of a millimeter. And then we have a large area enough that we can well focus even infrared beam like 1.5 micron. And this way we can get much higher efficiency. And that efficiency would range up to 20 to 30%. Because still my niobium nitride film is extremely small, so it was didn't absorb all the photons, and there was like fill factors about 50%. So there was still some photons which would travel through the detector unrecorded. So finally, the current commercial devices will have a resonant cavity, and so this way photons are kept in that resonant cavity, and can efficiency be like 97%. Well, here you can see some experimental fabrication of large devices. And small devices would give us that ultra-fast photo response on the order of 100. The longer devices, because of kinetic inductance, that a huge meander contains a very large inductance, and resulting in that large resistive region are typically on the order of a few nanometers, few nanoseconds photo response. Niobium nitride deposited typically at high temperatures, and you can see a nice epitaxial growth on a sapphire substrate. And experimental setup is extremely simple. Device is inside a dewar at 4.2 Kelvin. And you can take any source of light. You can have a flashlight. We happen to have femtosecond lasers in my laboratory, so we would use femtosecond lasers. You have bank of neutral density filters, and you could lower the intensity to that on average you have less than 1 photon per pulse, which will give you, and then we could easily count all those photons. I want to stress that if you look at the statistics, and that's a simple Poissonian statistics, so you see that for low number of average photons per pulse, probability of detecting a photon is just proportional to that average number of photons per pulse. So it's single photon detection and two photon detection. And you can clearly see that our experimental results follow perfectly. Of course, I changed the bias current so I could create be either very close to that critical current or farther away. So this way I could control my threshold. And you can see by controlling the threshold, I could have a detector which detects single photons, and this under this condition, the same detector would detect only photon pairs. Because, well, as you imagine, higher photon energy, the higher is probability of having the detection event. And you can now see that you can, depending, if you change the wavelengths, you have similar situation. More energetic photons will be counted one by one. And if you go to kind of an infrared, the same detector operating at the same bias will be a two-photon detector for larger, and then for lower photon averages will be single-photon detectors following that, that rule. Quantum efficiency, once again, it's about 20–30%. And you can see that at low temperature, if I go to high photon energies and 2 Kelvin, I have a saturation, and then I have a nice plateau, or I can reach the maximum quantum efficiency. Dark counts decrease exponentially with temperature, and you can see that for my bias, which is this one, dark counts at 4 Kelvin at, well, 1 hertz. But if I go to 2 Kelvin, well, they are essentially completely negligible. So quantum efficiency for visible light is about 30%. For communication wavelengths, and this is just a meander detector, no resonant cavity. So one can also couple it to a fiber, and there are different ways. We use the photoresist ring where we put the fiber and put some kind of a bridge. So this way, our device could pretend to be a room temperature device. Well, because your device inside it, the liquid helium dual, but outside you have the input in terms of fibers and output in terms of electrical connectors. So it would pretend to be the current, the latest, and that's, I got a picture from Single Quantum, which they make commercially single photon detectors. They don't use helium, they use a cryocooler. Here's their packaging. So this is a fiber, and the response is here. They can have up to 5 single photon detectors there. And please see what kind of performance they can guarantee when you buy. So this is silicon, this is single photon. Those are the indium avalanche photodiodes, and this is single quantum. You have nearly above 90% on quantum efficiency in a wide range of communication wavelengths between 1.3 micron to 1.55. You have essentially, and next you see you have 50 picosecond jitter. So this is really, really a dramatic jump forward compared to semiconductor devices, which were essentially kilohertz type devices, and again, with quantum efficiency, you can see 20%. Detectors, if they are made into multi-pixel arrays, can detect several photons under assumptions that two photons are detected if they don't hit the same detector. So you can see this is 1, 2, 3, 4, 5. This is a 10-pixel detector, and you can easily time resolve up to it's experimentally it would work nicely up to six photons. Another interesting feature is that very large meander, again, the black is niobium nitride, can act as a grid, as a polarization grid for optical photons. So my detector is sensitive to polarization. And here you can see we have two detectors, one with horizontal stripes and one with vertical stripes. And we focused our beam right here, and we flooded this one. So you can see, or let's say we do it this way. We focus on this one, so horizontal, and we focus on vertical. And you can see that the counts depend on the polarization angle. If you rotate these detectors, you can see that. And when you flood them with one large, then of course the polarization dependence disappears. So this is an interesting feature. Quite often could be used to have polarization sensitivity. Well, our friends at Delft, they fabricated also this kind of a funny detector where you can see that the detector stripes are winded up this kind of a spiral, and they could look at different places, and of course they could get horizontal polarization, vertical polarization, and 45 degrees. So, and again, if flooded, then there was no signal. In some cases, you don't like to have polarization sensitivity. You would like to catch all the photon, no matter what kind of polarization they have. And the group in Tianjin University in China came up with that panel curves that the detector was not simple stripes, but this kind of a section. And this way you can kind of see this entire detector. Then it was completely polarization insensitive. Some applications. I still have I believe I have 10 minutes. Is that correct? Well, do I have?
Yes, correct.
Okay.
It's correct.
Perfect. So let me talk about one historical application and a number of current applications. The historical application was because when actually our research with my group and a group from Moscow initially was funded by a semiconductor testing company, because you may not be aware, but in commercial CMOS circuits, as they get smaller and smaller, the switching of either NMOS and PMOS transistor is associated with higher and higher energy electrons. So those electrons simply start to get warm, and they emit thermal infrared radiation in nanoscale circuit that will be in the range of 1.2, 1.8 micrometer. And the group from Silicon Valley and they called the optical, they wanted to be able to see that emitted photon, because that would tell them how fast transistor switches. It's also a good detection mechanism, because if circuit has some faults, then the circuit will start to heat up excessively and will emit thermal radiation. Electrons will be accelerated and emit thermal photons more excessively. That was first studied by people from IBM, and they showed this kind of a feature. So you see, this is an inverter chain, and you can see that from time to time, this is simply 30 hertz type schematics, and you can see as signal travels, you see those blips of photons being emitted. Well, this is nice, but the group we worked with, they wanted us to sit in one specific place and now have that blips time resolved. So that was the challenge, to have a detector fast enough and sensitive to infrared that could detect that single photon as a function of time. So they built the entire system. They built the entire system with our device and put inside the cryocooler and bias it and everything, and would focus light being emitted from integrated circuit on our device. This is all being here inside and was large label non-serviceable parts. So operator, that was main customers were IBM, Intel, at that time also Motorola, because it was in business of integrated circuits. So operator was absolutely not aware that there was any superconductivity involved. Operator would put the chip here and test. And of course, the entire tester was $1 million. So expense for superconducting detector and expense for cryocooler was essentially negligible in terms of gain, in terms of performance, because you can see we could get the signals extremely well resolved, and you can see each peak 62 picosecond. And I must tell that we got very old. I mean, the company allowed us to show you and then later publish only relatively large feature size or line width size chips. So they could easily resolve signals of let's say that time would be like 7 nanometer type feature sizes. And you can see the histogram, it takes a minute. Previously, they used photomultipliers, and it took half an hour and never could see any PMOS response. And that was so that revolutionized the detection. And I need to say that these days, all VLSI chips are being tested after production. So then detectors started to be used commercially, and then NIST was the first to show that if you have incoming photons and if photons come from single source, then you can clearly have anti-bunching. You have no correlation. So never ever two photons can be detected at the same time if this is a true single photon source. Other groups would show ultra high sensitive for remote laser communication and in safe wavelengths and or deep space communication. Again, those are over distances of kilometers. Those kilometer range high resolution using single photon detection based on our detectors. And finally, there is a lunar program, which was the highest data rate, 20 megabits per second, and to moon, and it was a single photon communication. Again, it was not necessary. The detector didn't have to be single photon, but needed to be extremely sensitive. So the single photon resolution was a plus, and have high repetition rate and extremely dark count. So to be able to catch that very fine signal sent from laser astronauts brought to moon and used to initiate communication. These days, arrays are extremely large. You can have faster and single photon arrays, and you can see that those are really large arrays and multi-pixel arrays, and they work for imaging single photon sources. And another important aspect was real jump in performance of quantum key distribution. As you know, all quantum key distribution systems are based on single photon transmission and detection, and using superconducting single photon detectors, you could see, I will show that was top quality in gas, and you can see that the rate was like 2 megahertz, and the distance was, well, you can see like 60 kilometers. And now we can have the fiber length of up to like 200 kilometers, and the repetition rate to 10 gigahertz or 1 gigahertz. So this makes all cryptography really commercially feasible over long distances. So concluding, I want to stress that currently single photon detectors are almost 100% quantum efficiency when they are coupled with a cavity. Of course, when they are coupled into a cavity, they are not the broadband detectors. But for most of applications, people are interested in quantum communication, for instance, at a specific communication wavelength. So if you use a fiber, you usually are restricted to a single wavelength. So that's a not major problem. On the contrary, getting this kind of sensitivity and quantum efficiency is very desired. In general, they are not simple click. They allowed some statistical analysis. I didn't show that because I decided to focus more on first elemental properties and then very advanced properties of these detectors, and that they can be like polarization discriminators. They can also, multi-sectional devices now are used for photon number resolving and photon single photon imaging. And all started with that unique applications. So unique applications are, and let me say the outlook. At the moment, most of the community is happy with niobium nitride or tungsten silicide detectors working at helium temperature in cryocoolers because they are commercially available, they are very reliable, etc., and not that expensive. Research start to move into higher temperature material like magnesium diboride. Remember, that has 40 Kelvin critical temperature. And yes, successful devices were fabricated, but they're not as good because simply the development of magnesium diboride, the quality of films, and those need to be extremely, extremely thin films, is far behind conventional metallic superconductors. Finally, there is a future in niobium nitride nickel copper bilayers would have enhance critical current and speed. And well, there are reports on YBCO detectors, but again, YBCO again in bilayer with a magnetic perovskite seem to give better performance. But again, the reason is that you really don't want to go into very high temperatures because then you start to have very high thermal noise. So being at low temperatures is important. And again, YBCO has extremely short coherent lengths. So the size of the hotspot is extremely small. So all this makes these devices very, very difficult to fabricate, especially if you like to have commercial devices. So my epilogue, after 23 years, that paper applied physics letters papers we published in 2001, you can have, a long laundry list of applications. And what is even more important, as I looked yesterday, there are almost 2,000 citations of this paper right now. And there are 1, 2, 3, 4, 5, 6 commercial companies selling commercial devices. And you can see there are one in Russia, 2 in the US, one in the Netherlands, and then I showed you that single quantum system in Switzerland and China. So if you have like 150K and you plan to do experimental work in quantum optics, that's your way to go. Well, thank you very much. And I would like to thank all my collaborators over the years, starting with Moscow and in Rochester, and all different sources of funding throughout the years, which contributed to all this development, which now kind of moved out, at least of my hands, because I'm interested in more basic science, and it's now in commercial hands of people who just sell those devices. Okay, thank you very much. And I'd be happy to answer questions.
Thank you for a very great talk. Do we have a question towards given talk from the audience?
I have a question.
Yeah.
Go ahead.
Yes, so a very nice talk. Have you thought about having one of those single lines near to another single line, so you have one as a source and the other one as a detector?
Yes, and such experiments have been tried in order to show that if you have two very closely spaced detectors, let's say single wires for simplicity, and if you put single photon source, it would never be that two detectors may fire.
So I saw a picture that you show that when once the electrons, the pair relaxes back, they emit a photon. That's what I was thinking. So,
no, they emit phonon.
Photon.
No, well, I can go. It's a phonon, and an energy of that phonon corresponds to energy gap for superconductor. So those phonons are really low, energetic. Well, energy gap in niobium nitride is about 2 milli-electron volts.
Exactly.
So phonons, and so you won't be able to detect phonons this way.
I see. Okay, so you
need to have large photon energy on the order of, well, at least like half a electron volt to make a measurable, well, because in simplest way, your gain in the detector is the ratio between energy of your photon and energy gap of or coupling of Cooper pairs. So if I have a 2 eV and I have 2 milli-electron volts, I have the gain of that 1,000. So that's why UV light is being so readily detected and for a long time. And that's in general feature in also semiconducting detectors. Well, there is no problem to detect X-rays because they are so energetic. You actually worry that you can damage, the device can get damaged. And there is a problem measuring low energy excitations like infrared, and that our detector pushed the boundary from visible light into that communication wavelength and below.
Exactly.
Still, for visible light, I would still buy silicon detector.
Yes. Yes. No, I was just thinking, like infrared or far infrared, of the size of the gap, of the gap.
Yeah.
Superconducting gap.
Yeah.
So,
even if you think about, and that's simplification of YBCR, the YBCR is if you assign something like energy gap, it's not a S-type superconductor, but anyway, it would be like 30 milli-electron volt.
exactly. Yeah.
So it's extremely low.
So the problem would be just how to fabricate this YBCO
Yes,
structures.
it's a fabrication issue because, again, coherence length is an order of nanometers, and that makes that the hotspot size is in orders of nanometers. So the line would need to be few nanometer wide, and the technology is still not there. People cannot fabricate YBCR, ultra thin films, ultra narrow, and having, that 90 Kelvin or 93 Kelvin critical temperature.
Oh, okay. Yeah.
And,
exactly.
and again, from application point of view, if you buy a cryocooler, again, it's a question of money. You don't need to go into liquid nitrogen. You buy a cryocooler and you can use niobium nitride and now tungsten selenide silicate because it's more stable, and you have a commercial device which is room temperature in the sense that you could see that the fiber inputs and electrical output. So it's interesting for people sort of like me working in physics, but you guys who want to push quantum communication, quantum information, you have the best tool you can get if you want to do experiments. And you can pick one of the companies, and the price goes down because there are more and more companies, and they produce now really multi-pixel arrays and everything.
Just a quick question in the meantime. How about usage of mixture of helium-3 and 4? Because there is also kind of binding like Cooper pairs. You have mixture of helium-3 and 4. You heard about this mixture, right?
Yes.
Does anybody attempt to make even more sensitive single photon detector? Of course, it will be much more costly.
Well, I'm still not sure. You talk about the condensation. Yes, I'm still not sure how you get the readout, because here it's a simple electrical readout, which is essentially digital, logical 0, logical 1. Okay, and that makes things extremely simple because, for instance, in my lab we are now building a digital superconducting digital readout, which will be placed next to the detector, and will do the all initial early like correlations and statistics, etc. Because your output is compatible with conventional digital circuitry output.
I see. Well, you have Josephson junctions also in.
Yes, so we used to use SFQ circuitry, Josephson junctions, to do the readout from SSPD detector.
I believe if photon hits such mixture, it also changes momentum of this mixture. So you rather discover the presence of photon that was hit by change of dynamical state of mixture, because you have superfluidity phenomena. So in a sense, this photon energy will be converted to mechanical energy of superfluid in case of helium mixture.
Yes, I can see that, but still, issue of having, I'm looking from strictly user point of view, how you can connect that to, let's say, my computer.
That would be troublesome for sure,
And with this detector, you get an output which is essentially like you can send it optical fiber in, and you have train of pulses, which is logical 1, logical 0, and at the end you have train of electrical pulses, and you have logical 1, logical 0.
Yeah, I got your response quite much, but it was just a kind of academic question in a way.
Well, I'm looking again. I'm in the electrical engineering department.
I see.